How's it going, everybody? In this video, I am going to give a high-level overview of both MPLS Layer 3 and MPLS Layer 2 virtual private networks, or MPLS L3 and L2 VPNs. This comes as a request from several viewers via email that they wanted to get a high-level overview of what MPLS does and the details behind it, because MPLS is kind of one of those topics that isn't hit on until you get into the CCIE realm of routing and switching. If you're in the service provider track, you get hit with it pretty early on in the CCNP, as I'm actually in the process of studying for my CCNP, or I shouldn't say that, my service provider CCIE. That's currently my current track. I go back and forth between security and service provider. So what I'm going to do in this video is I'm going to give everybody a high-level overview as to the components that make up MPLS L3 VPNs and L2 VPNs and describe the differences between them, because a lot of the times you need the same type of information to get them to work. It's just that you need to make sure that when you're going through and setting this stuff up, you know what's needed where and why, because at the end of the day, if anybody can just Google something and then drop a bunch of config on a router and maybe or maybe not get it to work. So what you really need to focus on when you're looking at MPLS is understanding the different pieces to it, because unlike IGP like OSPF and EIGRP and BGP, MPLS itself is not a protocol. It is a service, and that's one thing that most people have a hard time understanding. Is same thing with BGP. BGP in some regards would argue that BGP is a routing protocol. Others, like myself, would argue that BGP is an application because it doesn't actually have that baked in information that is needed like IGP does. So, but that's a discussion for a completely different video. What we're going to be covering in this video as we go along here is pretty much the standard stuff for most of my videos. Is I'm going to cover some content regarding how all the pieces come together. So the first thing we're going to talk about is, once we get through the difference between L2 and L3 VPN, is going to be IGP and LDP and what each one of these does and why they're needed. Then we'll cover VRFs with route distinguishers and route targets. Then we're going to hit BGP, VPN-v4, PE to PE connectivity, and then we're going to talk about VRF aware routing with PE to CE routing. So the first thing we're going to talk about is going to be MPLS L3 to L2 and L2 VPN. And I almost said L3 to L2, and as far as I know, that does not work. So it really wouldn't make a difference in either way on how that would be set up. So what we're going to be talking about here in the first one is going to be L3 VPN. And the reason I'm bringing up that one first is because that's the one that's most commonly asked about. So when it comes to L3 VPN, this is the one that you're going to get the most exposure to inside of the routing and switching track. Whether you're a CCNP or CCIE, you're going to hear about this stuff, and especially if you're studying for your CCIE, this is going to be one of those topics that's going to be a pretty significant piece of your test. So I would definitely be very, very well versed in MPLS. So that's why you're watching this video, because you may or may not know much about it, or you may want, a different perspective on it. However, whatever reason you are watching this video for, I hope I can answer your question. So we do have a couple of people live on the video with me here, and they'll be asking questions, and hopefully I can answer those questions quickly. We don't have anybody that's typing them in yet, but we will be here soon. I'll have a Q&A section towards the end. And that's actually the 4 people that asked me to do this video are actually live on here. So if you're watching this in recorded format, I will be putting I'll go ahead and do that right now. I'll go back and I will put my contact information in here for you in case you want to get a hold of me, so you know who I am. If you've never watched any of these videos, you may not be a subscriber, whatever the case might be. So who I am is right there. And I am a CCIE and routing and switching, if you did not already know that. And you can get a hold of me, 82@yahoo.com. That comes directly to my phone, which you probably heard just going off a minute ago. Reach out to me whenever you'd like. So I'm going to go back to the breakdown as to what's going on here. Now, the the thing that most people have a hard time understanding, and if you do, I apologize, it's not very complicated, but I'll clarify while I'm here. The difference between layer 2 and layer 3 is this guy right here means it is IP routed, right? RTD. It's IP routed. Layer 2 VPN means that it's not layer 3 routed, but it's layer 2 bridged. So this guy right here is bridged. Now what's the difference between the two? Well, IP routed means that when you advertise a route from customer A site 1, we'll just say S1 here, and we'll do S2 over here. Simple enough. When you advertise a route from customer A site 1, that route gets injected into whatever method you're using for PE to CE routing. It gets learned by PE2, which is provider edge 2. And then that traffic there is then label bound. So for every route that you advertise into MPLS, a label is applied to that particular subnet, and I'll explain how that works here in a minute. And then it is forwarded over to PE3. PE3 learns it and then advertises it down to customer A site 2. Also, all of this is layer 3. So I could send a ping from here to here, and it should return. I could do a ping from the LAN segment over here to the LAN segment over here, and a ping should come back with 5 good exclamation points. You might lose 1 for the original ARP lookup. That's okay. I wouldn't freak out about that. The general idea here with this, with layer 3 is it's routed. So you need to have, this is a layer 3 routing protocol you're using. So that's going to be the main difference between the two. Bridged means that it is not routed. So basically what's going to end up happening is this connection right here and this connection right here will act like a giant switch. Okay, so I'm just going to draw a switch here, and so this is going to act like a giant switch. So you could effectively look at it like this. Customer B site 1 and customer B site 2, they both plug into this guy right here. This is what these black lines connecting to PE4 and PE1 respectively do. What you're doing is you're using the service provider's MPLS backbone like a gigantic layer 2 switch. So if you're familiar with taking a computer, plugging it into a switch, I'll draw a switch here, and another computer down here, and these two guys want to talk to each other, well, in order for them to be able to do so, well, it's supposed to be a nose, they need to be able to have some communication method to be able to do so. And this right here, the switch is a layer 2 device, which means they would be able to talk to each other through this on the same subnet. That's the other case in point. When you have these two connected via layer 2, they're on the same IP subnet. This interface right here and this interface right here do not get an IP address. Over here on PE2 and PE3 on this interface right here, they do get an IP address because it's layer 3 routed. They need an IP. So what you do on these connections right here is you point this connection right here to talk to this connection over here via what they call the XConnect feature. And we'll talk about that later on. And as somebody's mentioning, this is a variation of what they call Ethernet over MPLS. Yeah, that is absolutely correct. So that's the general idea behind that one. I'm not going to go through a demo, and there's a question about that. Are you going to be doing a demo? And I'm not going to do a demo. It's going to be a high-level overview. There's I might come back and do one later with the same topology, but just from a theory perspective, this is where we're at. So that's the difference between the two. There is one is bridged, one is IP routed, like this one here, and then the other one here is bridged. So it's these guys here. When you would go to, say, for instance, run EIGRP across this connection, what you'd be able to do actually here is, let's say you advertise this, let's say this is the 12.1.1.0/30 subnet, for instance, over here. So this is .1, this is .2. They're both on the same subnet. As long as they're both on the same subnet, what you'd be able to do, as long as the provider has done their job, on customer B site 2 should be able to ping 12.1.1.1, or I'm sorry, to 12.1.1.2 over here, and you should get 5 good pings. So it should come back like this. By doing that, then you can go here on this interface right here, and whatever the subnet is, type in 12.1.1.0, put your wildcard mask in there, and then you should form, over these two connections, an EIGRP adjacency, because they'll look like they're connected over to a layer 2 switch. that's what the idea behind Ethernet over MPLS. So that's the general idea behind that. So now that you've got a general idea of how the breakdown works, let's go ahead and take a look at this from a perspective of the details behind everything else. So it's not super complicated, it's just important for you to understand the details. So we're going to go ahead and get the ball rolling on that. Just give me a moment here to erase some of this other stuff here so we can keep this flowing nicely. So the first thing we're going to talk about here as we go along is going to be IGP and LDP. Now IGP and LDP, if you notice right here, I happen to have OSPF area 0. Okay, so that's the first thing we need to make sure we have going. What the main factor that we're going to have to pay attention to here is on the PE devices, we need to have a /32 loopback configured. Now, there's some debate on the internet whether or not you actually need to have a /32 loopback configured. And the answer to that question is no, you don't. What you really need to do in order for this to work is with OSPF, because of the way that OSPF is designed, you need to make sure that when you set up your loopbacks that you advertise your loopback addresses into OSPF. Now by default, OSPF advertises a loopback as a /32 host route, right? If you didn't know that, you're welcome. So it advertises a /32 host route, which automatically meets the prerequisite in MPLS for a /32 route. So it's a host route from end to end. So with that in play, let's say this is a /24, not a /32. That's completely okay. You could totally do that. What you could do is, if let's say this is a /24, but let's say for instance it doesn't come up the way it's supposed to, you can go underneath the interface, so interface loopback, whatever the number is, and you can type in IP OSPF network point to point. By doing that, you automatically advertise the route as a /32. The reason for that is because with point-to-point network type in OSPF, it does not advertise the subnet information. Which what I mean by that is it advertises the prefix, just not the length, right? It advertises that, but no length. It doesn't care if it's a /24, a /27, /16, /8, does not care. So what that'll actually enable you to do is go ahead and advertise it as a /32. It just advertises the IP address. Now, if you want to remove any doubt, use a /32 subnet mask on the loopback. Then you don't have to worry about doing any additional configuration. /32 subnet mask on the loopback, you're good to go. That is going to be needed on all 4 routers, on all 4 of your PE devices. Now, once that prerequisite has been met, and you have OSPF running on every link that I'm putting a check mark next to, the reason I'm doing the check marks here is so that you would know what subnets to advertise into OSPF. You're going to need to advertise OSPF onto all of what you would consider to be your internally forwarded routing. So what that means is anything that is not going to be forwarded out to a customer site or to an inter-AS connection. Meaning, let's say you had another, cloud over here, and let's say this is AT&T, and then you had Time Warner, or any other thing, and PE4 had a connection over here to PE5, and you want to do something like that. You would want to make sure that OSPF is running only on the links that are needed for MPLS, nothing else. So once you have all these routes advertised in here, you'd be more than happy to continue on to the next step. IGP is a required prerequisite to have up and running, and what they can say fully converged, meaning it has the routes have been advertised. Well, I shouldn't say the routes have been advertised. You have formed adjacencies between all of your routers in your MPLS core, which is all these routers here that I'm circling right now. You have also gone through the SPF algorithm, you've found your best routes, and you've installed those best routes into the IP routing table. So you can go to PE2 and do a trace route to PE4, sourcing it from PE2's loopback, and then you can forward across the network, and you get 1 or 2 hops depending on where you are on the network. So that'll be where you want to go. So the next thing you need to do, and there's a question, do you need to have a /32 loopback on the P router? No, you do not, because the P routers are not going to be touching the customer sites, so you do not need to worry about that. So That's a good question, though. That's a misconception as well, most of the time. What you can do then is, if you're using what they call a link state routing protocol, OSPF or IS-IS. Okay, this is the only two this is applicable to. When you're dealing with OSPF or IS-IS, both are link state routing protocols. We won't be touching on IS-IS here. We'll just be using OSPF in this example. What you can do with this guy is you can go underneath the routing process, and this is for all the commands and all of the demos that I would do later on. This would be for just iOS, not iOS XR or iOS XE. So straight router iOS. What you can do is from underneath the routing process, so router OSPF1 in this particular case, you can go underneath the process and type in the command MPLS Ldp autoconfig. What that command will do is it will automatically turn LDP on any interface that's already running OSPF. So if OSPF is sending hellos out a particular interface, LDP will also send hellos out that same interface. And this is assume if you do this all the routers in your environment, then at that point, as soon as OSPF converges, LDP should converge shortly thereafter. And then remember that trace route I told you to do between PE2 and PE4, sourcing it from PE2? So it'll look like it's coming from 2222 to 4444. Well, what ended up happening is once you turn LDP on, you won't route that via IP anymore. They will be label routed, meaning you will see the first hop here will show up as a label value, and this will only be the transport label. And I'll explain here in just a moment what the difference between a transport label and a VPN label are. There's two differences, by the way, and some change, some don't. What the difference between when you're looking at this is when you label forward, let's say this guy right here is a label value of 16, this guy here is a label value of 17. What you would see actually show up here, and actually it wouldn't show, this guy wouldn't be 17, this guy would be IP routed. The reason for that is when you go from PE2 to PE2 to P2, you would MPLS forward that. The reason for that is because you'd be coming across the link here, and because of the fact that this link right here is running LDP, you would automatically inject 16. Now 16, it could be 2000. The label number is arbitrary. It doesn't make a difference what the label value is. Depending on how you set it up, does. So you can set up a label range to allocate label ranges to it. So let's say a lot of times when I'm trying to figure out, when I first started learning MPLS, I would go to every router, and depending on the router number, would dictate what labels I associated to it. And the command for that is MPLS LDP or label range, and then you'd give it a range of say 100 through 199. And then you would do that, and then you'd be able to forward P1 would allocate labels 100 through 199. Now that only gives you that range, and anything beyond that, it would just allocate. It would start over again at, I believe, I'm not sure. I don't even know if it'll allocate any labels if you go beyond that. I never went above 100 routes, so I honestly don't know. So if you wanted to, if you're learning just from the beginning, that's a good way to start it. So you know which router is actually doing the forwarding. So by allocating this guy as an LDP route, you are no longer layer 3 routing it, you're label routing it. And label routing shows up at layer 2.5. So it comes right after your MAC address, but before your IP stack. So if you've got your MAC address table here, or if you've got your layer 2 header, so your source and your destination here. Right here is where MPLS would show up, and then you have your IP header. So this is your IP header, and then you'd have your source and you have your destination. And here is where MPLS would show up. So you'd have your 20 byte value for that, then you'd have your experimental bits for QoS, and you'd have your bottom of stack. Bottom of stack meaning there's no other labels to forward, because you can have multiple labels stacked inside of the forwarding, because you could be sending traffic to multiple destinations at one time. So as an introductory video to MPLS, that we're not going to get into the framing format right in this video. I've actually covered a lot of that stuff already. So you have that in play. So it's layer 2 forwarded, layer 2.5 forwarded. So the traffic comes across here to P2, and then what ends up happening here is P2 will actually strip the transport label off, and route it to the destination as an IP packet. Now, what that concept is known as is PHP, or penultimate hop popping. The idea behind that is if you are doing PHP, what will end up happening is if you're doing a PHP, you're stripping the transport label off and you're going to forward it via just IP or the VPN label, depending on the situation. Now, the transport label is how the traffic is forwarded through the actual MPLS core. So you have the transport labels on top, the VPN labels on bottom. The VPN label, this guy never changes. Whenever traffic comes into the network here from customer A site 1, hits PE2, what ends up happening is a VPN label is associated for every route that the customer advertises to the provider. The provider learns that route, and assigns what they call a label binding, assigns a label value to that particular route. The VPN label is what signifies the customer's traffic. And you'll actually see this if you do a show MPLS forwarding table. Any subnets that the customer has advertised to the provider, you will see a V sitting next to that particular subnet. That indicates to you that that is a customer route. Anything that doesn't have a V next to it is a connection that you have inside of your MPLS core. Now, with that being said, is the VPN label is associated and does not change. The transport label will change on a per label switch router hop, meaning PE2, PE1 through 4, and PE1 and 2 will all have a transport label associated to them. Depending on which route and depending on where the next hop is, will determine which one gets forwarded. So, to answer your question, the question is, how does that affect the forwarding through the network? Well, to answer your question, the way that MPLS forwards the traffic is based off of IGP conversions. So let's say let's assume for just a moment that you're completely converged, and the normal path, let me switch over to green, is this path to PE4. Well, let's say for instance that you are told by your boss, who doesn't know MPLS as well as you, says that he wants everything to go through P1 for whatever reason. He doesn't give you a good one. Everything's going to get routed through P1 to P3 to PE4. So you go this way is the new destination that he wants to. What will end up happening is the only way LDP will be able to forward your traffic the way you want it to is if you actually go to the interface of the routers and you make the traffic going towards P2 worse. So the interface bandwidth, the delay, the cost, whatever methods, or how it's done will be dependent on the protocol you're working with. So like for OSPF, usually what I do is I type in auto cost reference bandwidth and whatever the average bandwidth speed is on the interface. So if it's gigabit or 10 gigabit, whatever, that's what I apply in there. And then if I need to choose to make a path worse than another one, I would just use a lower bandwidth. It'll be less preferred then, because it'll based off the cost, it'll be incremented that way. When I'm dealing with EIGRP in the MPLS core, which I've never met a provider that uses EIGRP, it's usually ISIS. When I'm testing this out in EIGRP as the MPLS core routing protocol, I use the delay factor. The reason I use delay is because if you modify the bandwidth, that can mess up your QoS mechanisms. So if you're using bandwidth and you modify the bandwidth, you can throw your metrics and so if you're doing shaping or policing based off of the bandwidth, that'll screw you up, or change your metrics is probably the better way to describe it. So we have that. So as you're forwarding through here, what will end up happening is the transport label will change on a per hop basis. So as you're going through, so PE2 might advertise a label of 16 to get to P1. P1 might use 16 to get to PE3. And this guy might use 200 to get to here. And you'll actually see these guys show up. On every hop in the network, you'll see this number change. So you'll see 16, then 200, and then at that point, well, actually, you won't see anything here because this is the PHP. So it'll go 16, 16, and then you'll see, actually what it'll say here is it'll say pop. And pop means it's taking the transport label off and forwarding it via the VPN. So that's why that comes into play. The VPN label never changes. Now, based on how LDP associates the routing inside of the MPLS forwarding table will determine how it goes. So if this happens to be this link here and this link here both happen to come up first, and LDP forms an adjacency across those two, and they both happen to get a label value of 16, that's okay. Because with the way that MPLS applies is the label value is locally significant to that particular connection. So you could have 16 on all three of these because they are three separate subnets, three separate interfaces. Even if they're sub-interfaces, it doesn't make a difference because of the fact that they are three different subnets. As long as you have a different subnet, you can have the same label allocated, and that can be on both ends. So it could be 16 here and 16 here. It doesn't make a difference. It could be 16 across the board on every interface. That doesn't make a difference because of the fact that when you're forwarding traffic out, you're going based off of the next top label. It knows how to get there based off of the forwarding table. So as long as OSPF is converged, you're okay. Normally it doesn't work out that way, and when I'm setting stuff up, usually I use the MPLS label range in order to get the job done with that. So that's how that comes into play. So now that we have MPLS completely converged in the network, I'm going to go ahead and clear the screen. So because I wanted to kind of a little bit of detail on how that would actually work. Next thing we're going to talk about is VRFs and route distinguishers. Now, the thing with VRFs, route distinguishers, and route targets is you have to understand the reason why you need a VRF and what the route distinguisher and what the route target mean. Now, VRF stands for Virtual Routing and Forwarding Table. So, and there's a question: is the only way to assign LDP is through the MPLS autoconfig command? Sorry, that is not the only way. That's actually the easiest way. The MPLS LDP autoconfig command is only available if you're using OSPF or ISIS. If you're using EIGRP or RIP or static routes for whatever reason, the option you have is to go underneath every interface. So you have to go underneath these three interfaces and type in the MPLS IP command. By typing that in and doing that on every interface that's running a non-link state routing protocol, that's the only way to get MPLS to form across all of your connections. That's it's not widely used that way. That's why it's important to know. So does that answer your question? Cool. So VRFs with route distinguishers and route targets. A VRF is a virtual routing and forwarding table. What this allows you to do is this allows you to take the router and carve it up into multiple routing tables. So a VRF is to a router what a VLAN is to a switch. So a switch can have, you can take a switch and you have, you got all these ports connected to it. Each one of these by default is VLAN 1, right? That's just the way it goes. Well, you can go in here and you can create VLANs 1 through 10, for instance, and you can put every one of these ports. So you can put this one in this could be in 2, this could be in 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so you can put all these guys into different VLANs, and the cool thing about it is the connections between those connections won't be able to talk to each other unless you have a layer 3 device, whether it's a router that it connects up to, or you have the ability of doing inter-VLAN routing locally on the switch, which would mean it would be a layer 3 switch at that point. If that's not the case, then you have to send it up to a router, which will send the traffic up here on VLAN 10 and then out on VLAN 2, or whatever the case might be. It really depends on what the situation is. So you have that in play. So a VRF is a way of creating virtual routing and forwarding instances where that is analogous to a VLAN and a switch. So you create multiple VLANs on a switch to break up into different layer 2 broadcast domains. VRFs do the same thing. So typically what you do is you would create a VRF per customer. So in this case here, you'd have VRF and then you'd be able to name it. So it would be IP VRF, customer _A or something like that. This is for IPv4 only. Now, let's say, I have customers that have globally reachable networks, meaning that they have sites in, say, Brazil or the UK or in Australia, whatever the case might be. So Normally what I do here is I don't use IPVRF, I use Vrf definition. Vrf definition gives me the ability to run both IPv4 and IPv6 at the same time. And then I just give it the name customer A. And then I go here. Usually it's going to be whatever the customer's name is, so it could be Acme or whatever.com. And then from there, you're able to activate the IPv4 and the IPv6 address families. Now, what you do underneath the VRF config, this is where this stuff takes place. You would create the route distinguisher and the route target. Now, the route distinguisher is what is used to make the route unique per customer. So what you do is you create a value of some sort, and what the route distinguisher does is it gets prepended or added to the beginning before the route is actually brought in. It is created to make the route unique. So let's say, for instance, the customer over here is using 10.1.0.0/16 for all of its subnets, right? 10.1.0.0/16. This guy is also using 10.1.0.0/16 for all of his routes. Now, I have a question raised, and this guy is only a CCNA, not to knock you, but those are overlapping subnets. How can that be? Well, very, very simply. So the main thing that you need to focus on is when you're paying attention to this is when you have a situation like this, because of the fact that customer A and customer B had the same private addressing range, this is the most common thing that you're going to run into inside of MPLS VPNs. The route distinguisher is designed to take care of that problem. The route distinguisher is typically in the, you would see it is a value, value, and then subnet. So that's usually the way that that's usually how it's broken up. So this value right here could either be the autonomous system number and some unique value. It could be 1:1. It's really up to you on how you want to do that. Normally, I see it advertised as the autonomous system number of the customer. That's usually how I see it done. But that really doesn't make much of a difference. So the route distinguisher, these two, all this right here, each one of these colon sections is 32 bits. So 32, 32, 32. So this means in total it's a 96-bit address. That's when it's going through the MPLS VPN. By breaking it up like this, you can go in here and if you were to do a trace route and break it up into show IP route, if it's and see what it's broken down as, you'd actually be able to see the route distinguisher information plugged in here. This is per route. So customer A might have, we'll say, this is BGP AS 65,000, and you might have, let's say that the route distinguisher for customer A is 65,000 colon 10, and that's what you would do. You'd say RD underneath each address family if you're using a VRF definition. If you're under IPv4, it's only IPv4. You would say RD 65,000 colon 10, and then for every prefix that customer A advertises to you, you would see 65,000 colon 10 colon and whatever the prefix added. So in this case, it would be 65,000 colon 10 colon 10.1.0.0/16. That's how it would get broken down. So with that case in point, that means that anything you see come across, if you see this piece right here, you know it's coming from customer A. If you're not sure, you can do a show run VRF and take a look at what's going on. So that's a big case right there. The route target value. The route target value is specific to what particular PE devices you want to be able to send and receive traffic from. So the route target is going to have an import, which means taking, and I'll explain these here in a second, export, and then we have both. Now the difference between the three is when you're importing routes, you're taking them out of BGP, so VPN before BGP, and bringing them into the VRF. If you're exporting them, you're taking them from the VRF and you're bringing them into BGP VPN-v4. Okay, that's the most common misconception that most people have, is if you're taking them out of the VRF, they're being exported. If they're being imported, that means they're being brought out of. So that's the big thing. And if you use the both command, this basically is a macro, if you will, and it basically says import and export at the same time. When I set it up just to keep things very simple, when I first started learning MPLS, I did route target RT, or it's actually route dash target both, and then whatever I wanted to do. And the route target value typically is going to be the same as the route distinguisher, so 65,010, for instance. That's how I would do it. And that's what here is. And you can pick and choose using the route target import and export values which way the traffic is going to get forwarded. So typically, if I'm going to be doing it that way, I'm going to be setting it up to where PE2 and PE3 are going to be both importing and exporting 65,010. Now, BGP does this automatic filtering mechanism. And what they do is if you have a situation where if you don't have a VRF configured with a particular route target value, and you receive route target information from another PE device that doesn't match a VRF that you have configured, or an import policy that you want to be bringing routes in from BGP from, then it will get dropped. Simple as that. Now, is that a good thing or a bad thing? Well, depends on your situation. If you disable that, then you'll be able to go ahead and learn all those routes in regardless of where they're coming from. So that's more of the service provider side of the house, but for the route switch, it's usually okay. So the VRF gets placed per for every customer that you have associated to the PE device. You need a different VRF to be able to handle this. VRFs can be done on sub interfaces, serial interfaces. Doesn't make much of a difference as long as you have a layer connection to them. That's all that matters. Now, with that being said, the VRF is placed on the interface. So you put, actually I should say, the interface is placed inside of the VRF. Same thing with the switch port is placed inside of the VLAN. So they both do the application piece for taking the interface and putting it into the broadcast domain is the same theoretical breakdown. So what you do is you go to the interface level here of PE2. Let's say this is gig 1. You would go to interface gig 1 and you type in IP VRF forwarding is going to be customer A. Now, if you already have a IP address associated to that interface, it's going to remove it because it's moving gig 1 from the global VRF, or the global routing table, because VRF default means the global routing table where all interfaces start regardless of how many you create. It is moved into the VRF of customer A. Then you'd have to reapply the IP address. So typically, if I'm going to move a interface that's already in a VRF, or I'm sorry, already has an IP address configured, I do a show run interface, whatever it is, and then I see the configuration. The only thing that it removes is the IP address. The VLAN information, any type of QoS mechanisms you have in place, any additional configuration is not messed with. The only thing that is removed is the IP address. So you would simply just have to go in there and type in the IP address again, or copy and paste it back in, and you're good to go. So, and that's pretty much all there really is to it. And then if you're doing that's if you're doing IPVRF forwarding. If you're going to be doing VRF definition, you would type in VRF forwarding, and then whatever the VRF's name is. Same concept applies with the IP addressing issues that you can run into play with, and that's how it breaks down. So once this interface is in a VRF, then you need to have a VRF aware routing, and we're going to talk about that next. But I'm going to talk a bit more about VRFs. Now, VRFs can be a pain in the butt. So the most common question I get, and this is, since we're on the topic of VRFs, that's why I'm going to go on kind of a tangent. So let's say you have a router here, and you have a bunch of interfaces. It's going to look like a bug by the time I get done drawing it, but that's okay. The way that you're going to look at this is, we'll say this is a provider edge device, right? Actually, let me go ahead and erase that piece of it because it's not what I wanted to do. So, alright, so you have a PE device. what you want to do is you want to take, and let's go ahead and we're going to say these two right here are in the global routing table, right? VRF default. And you have, I'll say this is PE1 or PE2. So what you do here is on this particular device, you have these two interfaces are in the global routing table. You go then on this interface, let's say you have customer 1, customer 2, so 1, 2, 3, and 4, right? So you have these 4 customers. What you could do, and actually, let me take this a step back. Let me do this, because this will make more sense. Let's do this. What I'm actually, there's a question, what am I trying to accomplish here? I'm actually trying to accomplish VRF Lite. I'm trying to give you guys an idea of what how that breaks down. If you're not familiar with VRF Lite, that's okay. I'm going to break that down. I'll say this is customer 1 here, this is customer 2 here. Now the idea behind these guys is VRF Lite does the same thing as MPLS with VPNs. It takes and it creates multiple routing tables. Now the key thing here to understand between them is when you're dealing with VRF Lite, you have to look at it like this, and then like this. So the idea here is when you have two interfaces in the same routing table, those two interfaces can talk to each other, right? Same thing with VRF2, VRF1, VRF2, global routing table. They all can talk to every interface. It's if there's 2 or more interfaces, those interfaces can see each other. They can ping each other. They can send traffic between each other. It's a great thing. Now VRF Lite is great for trying to separate traffic between 2 different networks and not have them see their traffic at all. The beautiful thing about this is typically inside of education environments like universities and stuff like that, or you might even have hospitals. I've seen a couple of customers that they don't want to split off their network via VLAN. They want to do it via VRF, because this way here they completely separate the traffic, because it's just completely different routing tables, routing designs, all that type of stuff. And there's a question, what about multi-topology routing? You could do that, and multi-topology routing is one of those advanced features that isn't very widely deployed. That is where you would use QoS markings to determine which way traffic is going to take in the network, but that's outside of the scope of this video. So, with VRF Lite, you would simply create a VRF, either the IPv4 way or the IPv4 and IPv6 way. You would create a route distinguisher, and that's it. The benefit to doing this is you'll actually, where did my mouse go? There we go. Sorry, I lost my mouse. So VRF Lite would allow you to take and you can actually take the routers, and it doesn't have to be 6 physically disconnected links. It can actually be sub-interfaces. It can be one cable but multiple sub-interfaces. So as long as you've got .1q encapsulation and stuff like that, you can totally do this. I don't see this a lot, but it is a possibility in depending on the environment you're working in, to be used to completely separate traffic, just like a VLAN would be. This is commonly referred to as VRF Lite. VRF Lite is VRF without MPLS, in case you were wondering how that works. So that's the breakdown for that. Now, the key piece here that is necessary to understand is when you're doing this, if you're doing VRF Lite, it's locally significant to the router. If you're going to be doing VRF Lite and you want to do it throughout your entire environment, every router has to be set up this way. It's a pain in the butt, I completely understand that, but it's a necessary evil if this is how you want to go through it. I've never actually had to set this up in companies before, but the possibility is always there. Just be aware that the capability is available. Now, there's been a lot of advancements lately where you can do route leaking between VRFs using multi-protocol BGP, which we're going to be talking about up here in just a minute, but that's usually not utilized very often. There's also another one, and they refer to it as easy virtual networking, which does the exact same thing that VRF Lite does. The main difference between the two is when you're doing this, you don't go in there and set it up in a way of the VRF. What you would do is you would create, you'd still create the VRF, but instead of using a route distinguisher value, you'd use a VNF or VNet tag or a VNet trunk. The difference between the two is the VNet tag would be a .1q header value. So if you have multiple routers connecting together via whatever method, you would create .1q instead of creating .1q trunks and then putting every VRF on a per VLAN basis. You would simply go under and type in VNet tag, the tag value that would match the particular subnet, and then you would go in there and you would create, that would separate the traffic on the router, and then you would create on the interface, you would say a VNet trunk, and then what that would do is it would actually go in there and it's a macro command to create a bunch of sub-interfaces on that router to tag it. I actually shot a video of this. If you were to check out the CCNP videos in Evpn, I actually break it down and show you a demonstration of that, but I'm just giving you guys an idea of what capabilities are actually out there. So that's basically how that works. So that's what VRFs do and how they break down. There's a question. So on every router you want to run Vrf Lite on, you have to go in there and create the same VRFs, the same route distinguisher value, and all that type of stuff before it'll work. Correct. Now the route distinguisher is locally significant, so you can have multiple route distinguishers created per setup. It's up to you on how you want to do that. But if you want to run Vrf Lite, so let's say you've got 3 routers connected to each other, and you want to separate, staff from student, from say faculty, you could do that, and then you can each give each one a VRF, and then you would have a connection between these 2 routers, and then you'd have your connections as it breaks down. So staff, student, and faculty, and the same thing over here: staff, student, and faculty. What you would do is on here is you would take, so let's say staff is VLAN 10, this guy's 20, and this guy's 30. You would go underneath the interface, every interface, and you would create, so you'd have .1q, .10, .20, and .30. You would type in VRF, VRF staff, VRF student, and VRF faculty, and then you'd have to do that on the same router. So on this interface here and this interface here, as well as here, and then the traffic would be completely separated. This is where Evpn comes into play. This is what actually makes that transition process from one connection to the other much more simpler. That's where Evpn comes into play, because it's macro based instead of you having to type in the commands individually. So I would check that out. The Evpn video that I did definitely highlights that capability. So that's how that breaks down. So the next concept we're going to talk about here is going to be BGP VPN v4 PE to PE traffic configuration. Now, what this means is you have Virtual Private Network version 4. This is an address family inside of BGP. This is only done between the PE devices. So what this implies, in order for this to work, is PE2, well actually I should say it this way, PE1 through 4 would have to have a full mesh of BGP peerings to all the other PE devices. What this means is PE1 would have to talk to PE2, PE3, and PE4. And I'm just going to keep drawing a bunch of lines to give you the idea of where I'm coming with this. And actually, I think that's everything. Oh, no, PE4 to PE2. So it'd be a full mesh of connections. So that's one way you could do it, and then that would totally work. You don't have to have IPv4 BGP running in order for VPN v4 BGP to run. They are 2 separate address families. They do not need to be both running. If you want to run completely a VPN v4 and not run IPv4 BGP at all, you can totally do that. So that's going to be the main thing that comes into play with this. That's a definite option. Or you could do what they call hub and spoke VPN, is what I like to refer to it. So what you could do is you could set up P1, and actually before I jump into that one, the full mesh version, so the full mesh, is typically for what they call is the BGP free core. What that refers to as these 2 P routers right here. If you're doing a full mesh with BGP free core, it means that the provider core routers, so the P routers that aren't connecting to a customer, don't run BGP at all. They only run IGP, whether it's OSPF, EIGRP, RIP, whatever the case might be. That is all they run. So by doing this, they're able to go forward and be able to run just OSPF and then MPLS for their label forwarding. If you're going to use what I refer to as VPN-v4 route reflection, then let's say P1 here is a route reflector for VPN-v4, then he would have appearing to PE2, PE1, PE4, and PE3, right? And then that's all you would do. Any updates that PE3 gets from customer A site 2 that's going to be advertised to site 1 would get reflected up to PE from PE3 to P1, and then P1 would reflect that information down to PE2. Customer A would pick it up. That's the only thing that comes into play with that. So the route reflection means as long as P1 has the route reflector client command associated to all of its peerings to P1 through 4, then when any provider edge router would receive a route into its BGP table for that particular VRF, and we'll talk about that here in a minute, that route would get advertised into BGP, reflected up to P1, and P1 would reflect that down to PE, to the other PE. The reason why this is in play is because by default, if you receive an eBGP update from another BGP speaker, now this would all be considered to be eBGP because of the fact that it's two different BGP autonomous system numbers. By default, an eBGP update will not get reflected down to an iBGP peer. Because of the fact that iBGP uses a administrative distance of 200, you don't want to be using iBGP to reach an eBGP next top. That's the general idea behind it. So generally speaking, when you get this, you want to be able to reflect it to other iBGP peers, because PE3 and PE2 will want to talk to each other. But by having a route reflector in the middle here, PE3 he'll say, well, P1 is my route reflector, so I'm going to send the traffic up to him. P1 will then reflect that down to P2, and then PE2 will advertise that as an eBGP peer or eBGP route to customer A, and then our customer A site 1, and then everybody will be happy. So that's the general idea behind how BGP VPN v4 is done. Now, the key thing to understand here is VPN v4 is utilized to advertise the traffic, so MPLS routes from provider edge to provider edge. That is it. It's a extension built into multi-protocol BGP, and the general idea behind this is in order for your PE routes. So far we've covered IGP and LDP, and we've covered VRFs with our route distinguishers and route target values, and you guys seem to understand that. BGP is the key defining piece to making all of this work. If you don't have BGP in play here, everything we've set up so far else isn't going to work. Because what VPN v4 BGP is designed to do is take the routes that are coming from the customer via the VRF or through the layer 2 connections that we're bringing in over down here at layer 2 VPN. He's taking those routes and they're encoding them as BGP, what they call extended community values. The extended community value is used to take the information from the customer and advertise that over to another PE device. So the extended community value, a community, if you're not sure what that is just a string of characters, if you will, for lack of a better term, that are used to encode different values. So if you were to go, say for instance, BGP here is the PE to CE routing protocol, and you get a route in from customer A site 2, and you do a show IP BGP for whatever particular prefix. So the command is actually show IP BGP and then the subnet. And what you'd actually see is a gobbledygook output, and you see a bunch of information here. This information was going to have some things in it, what they call the route target, the route distinguisher, some advanced features. So if it's EIGRP that you've got routing in there somewhere, you'll see the EIGRP K value show up. In OSPF, you'll see like the domain ID. You'll see the route type. There's a bunch of information you'll see, and I've actually gone through this in pretty deep details in the CCIE stuff that I've done. So if you were to go out to INE's INE site and check out the All Access Pass, and go in there, you would actually see the videos that I put together where I break down what the routing information equals and what it means and how to break that all down. So you have that in play. Now, once you have PE to CE or VPN before PE to PE connectivity, if you were to do a trace route from PE2 to PE4, traffic is more than likely going to take this path. Remember, this hop right here is going to have a label value of whatever. It could be 16, it could be 3000. Doesn't make a difference. This next hop is going to be a connection to PE2 or P2 to PE4 will be via IP because the PHP process is kicking into play, and you will see the transport label get stripped off, and the traffic will be routed via the the VPN label. So BGP VPN v4 is an activated connection. So there's two ways of actually doing this. The first way is you would do a router BGP and whatever the AS number is. In this case, it's 1000. You would type in address family VPN v4 and hit the enter key. You've gone now into address family VPN v4, and you are now able to do what you need to do. So you would simply come up here and you would do a neighbor, or actually I shouldn't say that. You would actually go from the global configuration, you would type in neighbor, and then you would say, we'll say P1 is 1.1.1.1. Okay, you do 1.1.1.1. So you would type in neighbor on PE4. You would type in neighbor 1.1.1.1. Remote AS is 1000, and then you would type in address family VPN v4, and then you would say neighbor 1.1.1.1, and you would type in activate. The way that iOS is set up to do is it's automatically going to say neighbor 1111 is automatically going to say send. I had to think of the command, send community both, or send community extended, or I think whatever the command is. This is automatically going to happen. This is a default. By typing in neighbor 1111 activate, you've activated the VPN v4 address family. If you have already converged with IPv4, you're going to see a reconvergence happen. The reason for that is because every address family that you turn on later on is an additional capability that you're turning on. So if you go in there and say, for instance, P1, you turn on BGP, authentication for whatever reason, you turn that on, and then you do a peering between these two guys. If your peering is already up, right? So there's a TCP peering between P1 and PE4. Everything's good. You form an adjacency. You've advertised routes, and then you turn BGP authentication on. It's not going to affect anything. The reason why is because BGP authentication is also a negotiated capability. What will end up happening is if there's a reconvergence of anything in the network, you take the network down for whatever reason, you do a clear IP BGP star all or soft or whatever the case might be. If you do any type of refresh, the connection won't come up because of the fact that there'll be a BGP mismatch. So you'll need to make sure you have authentication connected on both ends of this line. Everybody will be happy then. So once you have either a full mesh with all PE devices connected to all the other PE devices, or you do a VPN v4 route reflection capability, however the case might be, doesn't make much of a difference. Once you have that in play, then you'll be able to start actually getting there. Because, like somebody mentioned here, I tried to do that and it wouldn't work. If you try to do a ping or trace route to customer A to customer A, site 1 to site 2, it's not going to work because there's nothing in here to get it there. So you have to have BGP VPN v4 PE to PE connections working in play. Now the key thing in here goes back to where we were talking about IGP and LDP. Remember that loopback that I was talking about? That loopback is where you're going to actually be forming the peering to. So as long as PE2 can do a trace route to PE4's loopback, sourcing it from PE2's loopback, and the trace route comes out good, you know you're in good shape. So there's a question, what happens if it doesn't come out good? What happens is I get three sets of asterisks, and then it finally gets where it's got to go. That to me sounds like an MPLS issue, because the fact that you're already running MPLS because you're following along at home. If you're having that problem, I would go to all your provider devices, so all of your label switch routers, regardless if they're on the edge or on the core. I would do a show MPLS forwarding, and I would do a show run, or do a show IPsef, do a show MPLS forwarding table. There's a couple different things you need to pay attention to. If Ceph is turned off, that's one thing I forgot to mention, is IPsef has to be turned on globally. This should be turned on by default, but it may not be. IPsef is needed in order for this to work. So IPsef, make sure that's turned on, and make sure that MPLS, or MPLS IP or MPLS Ldp autoconfig is configured on the router on any interface in the core that is needed. If you have those in play, you're in good shape. After that, you might have a routing mismatch. You might not be advertising the loopback in. That could be the other thing. A lot of times, if you're not advertising the loopback in, then you'll run into problems with PHP will kick in one step too soon because you're going to be appearing off of this interface right here instead of the loopback. Yes and no. The question is, when you're dealing with the /32 host route, can you run into filtering issues? Yeah, and yes and no. Depending on how you're filtering can determine how you forward. If you're doing any type of filtering in your network, I would make sure that the host routes for your PE loopbacks are /32. They can't be /24 because it won't work. And don't do any summarization that's crazy. So just make sure that as long as your loopbacks are good, you should be fine. So now that we've covered LDP and IGP, VRFs with route distinguishers and route targets, and we've covered VPN before, PE to PE traffic. Next thing we're going to be talking about is VRF aware PE to CE routing. So this one here, not too crazy, but it's still important to know. This piece right here is going to be specific to anybody that's running this inside of production. So VRF aware connections are actually going to call back to, has the interface been placed inside of the VRF? So do you have gig 1 here actually inside of VRF customer A? If the answer to that question is yes, then you're good to go. The first thing I'm going to talk about here is BGP. I'm not going to go into a deep dive on how this stuff works. More high level, just to be aware of this. Because you're going to be running BGP already internally for PE to CE, or actually PE to PE traffic. So I'm just going to draw a circle around these 4 PE devices. Because you already have BGP VPMD4 running between PE2 and PE1, PE3 and PE4, or if it's route reflected, your method is pretty arbitrary in how it actually gets in there. If you're running BGP between the PE and the CE, you don't have to do anything else. Just get the customer A traffic to be get customer A, site 1, and site 2 to talk to each other. At that point, you're in good hands. As long as these guys are there, that's all you need to worry about. Beyond that, you're in good shape. The point here, because of the fact that they're the same protocol, they're going to automatically advertise information. So any routes that you advertise into BGP, whether you're doing the network command, you're doing you're calling a prefix list and redistributing that via route map, whatever your method is to get it into BGP. As soon as you advertise that to here, what's going to end up happening here is PE2 is going to receive that route, and then as long as PE3 has a route target value set up to import routes that PE2 exports into BGP, and those routes are imported into the VRF for PE3, you'll be in good shape. Customer site S2 will pick those routes up, and then routes will show up as BGP routes over here, assuming that this connection right here is BGP as well. There's a question, can you use multiple routing protocols for PE to CE routing? Yes, you can. I believe you can use all of them. RIP, EIGRP, OSPF, BGP, and IS to IS, and static routing, as a matter of fact. So that is definitely a possibility as well. So as long as you have all those pieces in play, VRF aware PE to CE is actually pretty simple, but it's a necessary evil when you're going through setting stuff up. So if it's BGP, you have nothing to worry about. If it's any other protocol, you do have other things to worry about. So let's say, for instance, you decide to run OSPF. So OSPF as a PE to CE routing protocol can be a little sticky, but I'll break down exactly what you need to do. Your connection between customer A, site 1 and PE2 is a standard OSPF connection on this side. On PE2 is where the fun begins. So if we're running OSPF process area, let's say we're using proc 1 here. On PE2, you're also more than likely using proc 1. For your VRF configuration though, so Vrf Setup, you need to create a different connection for this. So what I would do, if I was you, is if you're using proc 1, which most people do, you're going to need a different process number for this connection here. You're going to say, this is going to be router OSPF 2, because this right here is the, the process number. You're then going to come into here and you're going to type in address family, VRF custom array. Because then you're going to be going underneath the custom array configuration with OSPF process 2. This is where you're going to type your network command. You're going to type your network command in here, and whatever the subnet is that you're going to be trying to advertise into here, or actually whatever subnet you're trying to run OSPF on, that's going to form this OSPF adjacency here. And those routes will be learned in as OIA routes on this side. If this guy here is running OSPF as well, you do exactly what I said here. You type in router OSPF 2, you type in address family VRF custom array, you type in the network command. What you need to do then is, since you're already under the address family VRF configuration, you need to type in redistribute BGP BGP 1000 subnets. That's what you need to do. It's going to redistribute BGP from this is going to be the redistributing VPN v4 routes from v4 from BGP into the VRF. You also need to go under and type in router BGP 1000. You need to type in address family VRF custom array. You need to type in redistribute OSPF 2. What will end up happening then is you'll be able to bring OSPF routes into BGP. Once you've done that, and you've done that the exact same thing here on PE3, then any routes that customer A has advertised to PE2 will then be able to get propagated into VPN v4, which will get propagated to PE3. They'll get redistributed from BGP into OSPF. OSPF will then advertise them to customer A site 2, and then all those routes will show up as OIA routes. Same thing over here. Anything that customer A site 2 advertises as a customer A site 1 shows up as OIA. Now there's a question. Why? Simple answer. Because of the fact that OSPF is running inside of the VPN core here, what this becomes here is the MPLS super backbone. The key factor here is customer A site 1, this router right here, and customer A site 2 right here will become OSPF endpoints. PE2 and PE3, respectively, will act as area border routers on both sides, so ABRs. By doing this, you act here as a completely separate area. Okay, so it's like you are trying to connect, and this could be area 0 as well. So don't get confused here. This could also be area 0. It doesn't make a difference. But because of the way that OSPF is set up and the way that it breaks down inside of the network, this guy becomes a super backbone. So the MPLS core is a super backbone. You then take that information and then you advertise it likewise. So this becomes a inter-area route. Now what's actually kind of cool about this, and you may or may not agree, is you actually could have a directly connected link between these two. So let's make this green. You could actually have a connection here. Let's actually go a little bit, go medium thickness here. You could have a layer 2 connection of some type. Okay. Go to thin and go back to black. you could have this guy right here could be a point-to-point connection of some type, and whether it is a it doesn't make a difference. It could be a point-to-point fiber connection, a layer 2 connection of some type. Because of the fact that you might be running area 0 over this guy right here, what will actually end up happening is, because this guy will be seen as an OSPF route, which is referred to as what? Any ideas? Because I know I got a couple CCNAs on here. I'm just curious to see if you would know what that would be advertised as. That is close. It's but no. The answer to the question was it would be an inter-area route. Anything that's OSPF area 0 should automatically be an intra-area route. Because of the fact that OSPF, the state machine goes O, OIA, and then OE2, OE1, ON1, or ON2, ON1, because that's a state machine. Because it does it like that, what it will actually do here is it will prefer this path here because it is an intra-area route. If you want it to be the other way, PE2 to PE3, you would actually configure a sham link between these two. A sham link is like what a virtual link is inside of regular OSPF. So if you have an OSPF area, and so this is area 0, you have area 1, and then you have another area right here, this is area 2. Because of the fact that area 2 is discontiguous from area 0, what you would end up doing here is this ABR here and this router right here, which is not an ABR by the way, only a router with an interface touching area 0 and an interface touching another area is considered an ABR. You would actually tell this router here to connect to this guy with the virtual link, and this guy here with this guy with the virtual link, and pointing to the router IDs. They form a virtual link between these two. Area 1 acts as a non-backbone bridge between area 0 and area 2. So area 0's range, I guess you would say, their reachability becomes covers area 1, then area 2 is able to touch area 0. This guy becomes an ABR, and then all of a sudden area 2 will learn routes. A sham link is doing the same thing, except for you're doing it between the PE devices. You, as the end customer, have nothing to do with that. I have a friend of mine who lives in the New York area. He is also a CCIE. A good buddy of mine. We actually took the exam together on my 3rd attempt. Actually, the first time I met the gentleman. Really, really smart guy. He actually, the company he works for, he actually had this running, and I think there's an RFC 42. I want to say 4279. Don't quote me on that one, but if you were to Google OSPF sham links, there's actually a RFC for that. He had it running in his environment, and he pulled it out. So kudos to him for doing that. It clears a bunch of stuff up. Here's a question: why would you do that? Simple answer. Anything that happens in an area, so link up, link down, anytime SPF has to run for a new calculation, any routers in that area have to run the OSPF calculation as well, because of the fact that type 1 and type 2 LSAs are significant to that particular area. If you happen to use a sham link, let's say you do this for all of your connections, so you have multiple sites. I'm just going to draw a bunch of circles here, and they're all connected via MPLS. So you have one gigantic area 0. This could be 1,000 sites. If a link flaps here, so you shut no-shut interface, that information is flooded to everybody in your entire environment. So that means that every site has to run OSP or SPF. That is a huge issue. You could have major reconvergence issues. Definitely not a smart idea. So I highly recommend, if you're going to use OSPF as your PE to CE routing protocol, keep the super backbone in play. Let these guys be inter-area routes. If you have a dedicated point-to-point connection that you want to run OSPF over and have the MPLS circuit as a backup, totally doable. And to answer your question, no, you cannot choose the inter-area route over the intra-area route. The state machine has a specific order of operations. You cannot modify that. So that is the key piece of information for you to all remember. So just be cognizant of that. So that is pretty much how all this breaks down. So let me take a couple of minutes here to wrap this up and what we're going to break down is layer 2 VPNs, because that seems to be the most common thing that I have people ask me about that are outside of the scope of the routing and switching exam. Layer 2 VPNs are a pretty unique situation, and I've pretty much already covered it. But basically, like I said, you're actually taking this connection here. Let me go to thin here. This connection here is coming up here, and this guy here, actually, let me do it this way. It'll make more sense this way. These connections right here are actually working as a gigantic switch. So you have the arrow here, and you have the arrow here. So these provider edge devices are acting like a gigantic switch. So the PE1, P2, and PE4 are acting like a gigantic bridge. You plug your customer, what they call the attachment circuits, into the PE devices on both sides, and this is supposed to be AC, not CA. You attach it like that, and then you're able to, as long as customer B, site 1 can ping site 2, you know you're in good shape. If that's the key piece right there, then you know you're in good shape. Then you can form an adjacency over that. Everything else that I talked about so far with your connectivity needs to be in play. So your IGP and LDP, that needs to be in place. Your VRFs, the route distinguishers, and route targets need to be in play. And then you also need to have your BGP, VPN, V4, PE traffic enabled. The only thing you don't need to worry about with layer 2 VPNs is your VRF aware routing. That does not come into play with it. So that is going to be the key piece of information for you to understand that once you have that in play, because this connection right here is going to be acting as layer 2, not layer 3. So if you have a situation like that, you're going to go on PE1, and on this interface, you're going to go underneath the interface of, say, interface gig 2, and you're going to type in the xconnect command. Xconnect basically is acting as a layer 2 bridge, and what you do here is you type in I don't remember the command off the top of my head. It's like xconnect, and then you say encapsulation MPLS, and then you point it to the loopback that you can reach from PE1 to PE4 with, and you say, to loopback of PE4, so we'll say 4444. You do that, and then what you do at the end of that is that piece right there, when that's done, you actually form what they call a targeted Ldp session with. The targeted Ldp session, what that does is it tunnels the traffic across the VPN core like this, and then at that point you're able to ping, and everything is encapsulated in Ldp. So that's going to be the key piece that most people have a hard time understanding. And there's actually a really good video on this. A gentleman by the name of Terry Vinson put it together. If you were to look up Ethernet over MPLS, that's the video that he did. And really, really good stuff. It's actually how I learned it, was watching his video. And it made a lot of sense. So it doesn't take a huge topology to make this stuff work. You just have to have a topology that's functioning to work. And to answer your question, yes, when I did it, I did it in GNS3. The connections came up just fine. I was able to peer. I pinged, and then all of a sudden I formed an EIGRP adjacency. Everything was great. It worked out just fine. So my topology, I think I will go ahead and set up a topology like this just so you guys can see how it works, and then go through the steps of configuring it. But I wanted to go through a thorough breakdown as to how all the pieces come together, because I feel like that's the thing that most people miss when they're looking at MPLS, is they don't know how all the pieces come together. Because the fact that it is the way it is, that's the piece that most people have a hard time understanding. As long as you know the four pieces to getting MPLS operational, then you're going to know what to do to get them in play. If you missed one, that's a good way to check. I always work my way from the inside. I work my way out. So I configure IGP and LDP. I get that configured, and then I go in and I do IGP and LDP. Then I do BGP, VPN v4, and then I do my VRF configuration, so VRF. And then in the VRFs, I create them, so the route distinguisher, the route target, and then from there, I go in and I actually apply the VRFs to the interface, so VRF application. And then once I'm there, once I have the VRFs where I need them in play, I can then go ahead and worry about my PE to CE routing. I've never had a customer do anything other than BGP, so I've never had to worry about it. And I would never ever recommend a customer do anything but BGP, because that's what the provider is more than likely going to be running on their side. You would have to have, in my opinion, a very specific reason to be not using BGP, because you can do so much with BGP already. It just makes more sense to me to go that route anyway. And a lot of times a provider won't even run a non-BGP protocol with you. So if you want to run RIP, they're probably going to ask why. You might have your own justification, but it might not be good enough for them. So with that being said, that is a very thorough breakdown as to how all this stuff works, minus the actual configuration. And then there's a question, do you have to do the Xconnect command on both ends of the peering? Yes, you do. As a matter of fact, you might even have another connection here and another connection here that you want to have on the same layer 2 bridge here. So PE1 and PE4 might be the bridge between the two connections, and you might have 30 sites associated to that. As long as you have the Xconnect command on the interfaces configured correctly, and then if they can reach each other, and those particular routers are on the same layer 2 subnet, you'll be in good shape. So that is pretty much where it sits. Yeah, the question was, am I going to create some videos on that as well? Yeah, I'll probably go through and I'll probably do like 10 or 15 routers like I have here, and I'll go through and I'll set it up so you guys can see what it looks like from a layer 3 perspective and a layer 2 perspective. And I mean, it won't be a super deep dive, but it'll be more high level, you know, just getting MPLS VPNs working, and then you know, what layer 2, what does Ethernet over MPLS look like? Because like I said, I am studying for my service provider CCIE, so we have a lot of that. Actually, I am looking to do a 4 to 6, maybe 4 to 8 video series on IS to IS coming up here soon, because like I said, I am doing that. I'm actually currently going through the CCNP service provider. I'm cracking that guy out here in probably a couple of weeks, and then I'll be moving on from there as I study for my CCIE service provider. So, and there's a question: why route switch to the service provider? Why such the quick jump? Mainly for the fact that it's simple stuff. I mean, you got to figure when it comes to core routing, I'm already an expert in that. When it comes to intra AS, which is what this is referred to, MPLS VPN, already an expert on it. Already can do it. There's a few caveats that I have to learn, like Ldp Session protection, Ldp authentication, some other things. The piece that I don't know is the inter-AS VPN, the traffic engineering, the multicast, and the layer 2 VPNs. So that's the one. There's like Lisp and L2TPv3 and .1Q tunneling. There's a few things that I'm not really strong in, and that's what I want to be studying. So for those of you that are looking for certification advice that are really strong in some areas, keep touching the areas you're good in, just to keep that knowledge level up, and you know you're crisp on those technologies, and you know the commands to get them working. Spend the majority of the time on the things you don't know as well, so you can bring those areas up, so you become, you know, really quick. You know, because you got to understand something. Not everybody is willing to go after a CCIE, and I understand that. But from a dedication perspective, you need to make sure that if you are serious about learning a particular technology, start from the ground up. Learn, you know, do some marketing terms. You know, what does MPLS stand for? Multi-protocol label switching. What are the different characteristics that it can do? Why was it created? Who created it? What are the details behind it? And just start taking one topic at a time. You know, and then next thing you know, you'll learn one topic, and then that topic will open up into, say, 3 or 4 others. Then you'll have that topic will open up to 3 or 4 others, and then you'll have it go down even deeper. Before you know it, you're 7 or 8 levels deep on just one topic. And then you'll be able to say, okay, now that I've completely exhausted this guy, I can collapse all these and go on to the next one. And then break it down, and then break it down, and break it down, and break it down, and break it down. It's just going through the material. It takes a long time, but at the end of the day, you'll be able to do what I just did in an hour and a half. I completely broke down MPLS to what I consider to be a pretty detailed breakdown, but I didn't go into any configuration. I didn't go through any type of really complicated designs. It was a lot of high-level stuff, but it's all off the top of my head. It's one of the topics that I spent the most amount of time on in the test, or in my test preparation, I should say. MPLS in the exam wasn't very difficult at all, but to be honest with you, for those of you that are looking to study for your CCNP or higher, like CCIE stuff, if you go into the exam and you're struggling with things, you're not ready yet. That's as simple as it is. You need to be really good in all areas of the test before you even think about scheduling the test. Just my opinion on the situation. So that is it for this particular video. I will be putting out more content in the near future. If you would like to know more about it, please let me know. My contact information is right there. I'll actually zoom in real quick on it just so you guys get a better look at it. My contact information is rriker82@yahoo.com. My CCIE number is sitting right there. That's just there to validate, who I am, in case you guys were curious to see how that breaks down. I hope this has been informative for you. I would like to thank you for viewing.